There's a lot going on in this question, so let's just read through really carefully. So we have a plank of mass capital M and length 2a. 2a is indicated on the diagram with its end A against a rough horizontal wall. So that is supporting it. There's going to be friction on the wall. Plank's held in a horizontal position by a rope. That's this line here. One end is attached to the plank at B and the other end is attached to the wall at C, vertically above A. Then a small block of mass 3m is placed on the plank at the point P, where AP is equal to X. That is also indicated on the diagram. I'm just going to start adding forces onto my diagram now. So I'm basically going to be considering the block and the plank as one unit. So there's going to be a weight acting down that is 3 capital M G. Note that there is no normal reaction here because I'm considering them as a single unit. I'm not looking at the forces on the block. I'm looking at the forces on the block and the ladder altogether. So, of course, you could have a normal reaction from the ladder on P, but there would also be an equal and opposite one on the ladder from P, and they would cancel out. So we can just ignore it. Plank's in equilibrium in a vertical plane which is perpendicular to the wall. So essentially we're working in 2 dimensions here. And then the angle between the rope and the plank's alpha, where tan alpha is 3/4. We'll come back to that in a second. It's modeled as a uniform rod. Right, I can bring this in now. So I know that there's going to be a weight from the plank acting in the very middle. And this is going to be capital M, G. And then that length is going to be A from little a from A, and it's going to be little a the other side as well. It might not look the same, but I've just tried to keep it a bit further to the left in the block. So I will add them both on. And we've just got to think what other forces there are now. So because it's been held up by a rope, there's going to be a tension going in this direction, capital T, set an angle. And then finally, there's going to be some forces from the wall. Now, there must be a supporting force pushing back because otherwise there's no way it will be in equilibrium. And I'm going to label this a normal reaction. So R capital A. And then finally, because we know that the wall is rough, there's going to be a frictional force. It's just whether the friction is up or down. It kind of makes sense that it's going to be up because surely if it wasn't there, it would just fall down. But we don't know for sure. Well, we don't know just by looking at the forces because there are downwards forces and upwards forces. Um, However, the way to really check it is just don't actually do it, but think about taking moments at B. Then there is no force from T anymore. There's just going to be an anti-clockwise moment. So there must be a force here to create a clockwise moment. So it's definitely going up. And I'm going to call that FA. And that's pretty much our setup. The only extra thing I need to do is use the tan alpha is 3/4. So I'm going to create a little triangle here. 3, 4, 5. Sine alpha is then 3/5. Cos alpha is 4/5. This sort of setup is absolutely vital for seamlessly doing this question. If you struggle with ladder problems, and it is one of the trickier mechanics topics in my opinion, then please remember this is one of the tougher questions. It's a bit unseen. You know, we've got ropes, we've got planks, we've got weights on the plank, we've got a rough wall. Okay, if you're struggling, and go back and practice some of the other ones where you just maybe got a ladder resting against a wall, that kind of thing, or a ladder against a rod. I mean, they're all different. That's the thing. It's just a case of practicing them all. But then I'd say come back to this one. But this is our setup. And the next step actually proceeds in the typical way that all ladder problems do. We're going to take moments about a point. And it's asking us to show that the tension is equal to this. So we could maybe take moments, well, not maybe, we're going to take moments to just have capital T as an unknown. I mean, we don't know what capital M is, of course, or what X is, but our answer is in terms of those. But we want to eliminate the friction and RA. So we're going to take moments about A. Always pick a point that's going to make your life as easy as possible. And generally, taking moments will just eliminate things much quicker because if we take moments about A, there is no component from FA or RA because the distance from the pivot is 0. So remember, for our moments, it's the perpendicular component of the force times the distance away from the pivot. Let's take a look at the clockwise moments. We're going to get capital mg for one of the forces, and then I'm going to be timesing by a. That's going to be the moment due to the weight of the plank. And then I've also got a clockwise moment coming from the block on the ladder, and that's going to be 3 capital mg, and then I'm going to be timesing through by x. And that is going to equal the component of the tension acting vertically times by the distance from the pivot, which is 2a. So if I take this tension, I can split it into this horizontal part and this vertical part. And if we want the vertical part, I'm just might leave that on the diagram actually. It's just to show that I've split T up. No, I'm going to get rid of it in a second actually. And the vertical part is going to be T sine alpha because it's opposite. It's opposite in this right angle triangle. Then the horizontal part would be T cos alpha, but that doesn't come into that doesn't apply a moment because it is not perpendicular. So I am going to get T times sine alpha, which is 3/5, and then I'm going to be timesing by 2a because that is the distance from the application of the force to the pivot. Right, we're pretty much there actually. We just got to rearrange and factorize things out. Let's do it in a few steps. So I'm going to times through by 5, and I'm going to take mg out. And then I'll be left with a plus 3x. And that is going to equal t times 6a. And the next line brings it all together. So it looks complicated. And of course, if you get stuck with it, you can still carry on with the rest of the question. T is going to be 5 mg 3x plus a over 6a. Nice. Now we're told that the magnitude of the horizontal component of the force exerted on the plank at A by the wall is 2 mg. That there is my RA that I had before. We're asked to find X in terms of A. So what you typically do now is resolve forces after dealing with the moments. And that's exactly what we can do. We can resolve horizontally. So it must be that RA, which we know what the value is equal to T cos alpha. I'm just going to write that first of all. They're the only forces that have horizontal components. Remember, we're splitting that tension up, and now we want this horizontal part. It's adjacent to the angle. So therefore, 2 capital Mg is going to equal, remember, we've got cos alpha, it's 4/5. So 5 mg 3x plus a over 6a times 4/5. I can cancel out mg. I'm going to times through by 6a, so I will get 12a equals 4 times 3x plus a, because I've times that 5 by 4/5. Let's multiply this out. I'm going to get 12x plus 4a. And that means that 12x is going to equal 8a. So x is going to be 8 over 12a. I can divide through by 4. It's going to be 2/3 a. I've managed to get x in terms of a. The force exerted on the plank at A by the wall acts in a direction which makes an angle beta with the horizontal. So what this is saying is that I've separated them into the constituent parts, the vertical and the horizontal part, but you could then add them together and you get it going in this direction here. And we want to find this angle here, beta, with the horizontal. So we've actually got what RA is. We just need to find FA, and then we can draw a triangle and do some trigonometry to work out tan beta. That's the plan. So let's resolve forces vertically now. I'm therefore going to get FA plus the component of the tension acting vertically, that's going to be T sine alpha, and that is going to equal the weight of the ladder plus the weight of the block that was on there. Brilliant. And that's going to be 4 mg. So now let me sub in for the tension, knowing that x is equal to 2/3 a, so we figured that one out. So Fa plus 5 mg, then 3 times 2/3 a plus a over 6a times 3 over 5. So all I've done here is sub in for t sine alpha, replacing the x by 2/3 a, and then that is equal still to 4 mg. So just need to tidy this up. The 5 and the 5 are going to cancel. Let me just work on this. So I'm going to get 3 mg multiplied by, now 3 times 2/3 is just 2. So it's 2a plus a, it's going to be 3a. And then I'm dividing by 6a. The a's are going to cancel. I've got 9 over 6, that's going to become 3 over 2 mg. And hence Fa is going to be 4 mg minus 3 over 2 mg. It ends up being 5 over 2 mg. Brilliant. So we can bring it together now. I've got my frictional force that's going up. That is 5 over 2 mg. I've got my normal reaction going to the right, which we were told, remember, was 2 mg. And then my resultant that they're talking about is here, and we want to find this. Well, actually, we want to find tan beta. So tan beta is going to be 5 over 2 mg over 2 mg, opposite over adjacent. The mg's cancel. We're going to get 5 over 4. There's one final part to this question. So we're told that the rope will break if the tension in it exceeds 5 mg. Explain how this will restrict the possible positions of P, justifying your answer carefully. So for this, I need to return to our general equation of the tension, not the one where we found out what A was, because that was for a very specific position. So T equals this from 4, and we require T to be less than 5 mg. So I'm just going to then sub in 5 mg 3x plus a over 6a must be less than 5 mg. Remember, m and g are both positive, so we can divide through by it. We'll just end up with 1 here. So it must be that 3x plus a over 6a is less than 1. Let's keep going. That means that 3x plus a must be less than 6a if I times through. Again, a is positive. So 3x is less than 5a, and x must be less than 5 over 3a. Let me just check. Did it say the tension could equal 5? I might have made a small mistake. So it can't exceed. Okay, I need to slightly modify this. We require that it's less than or equal to in all these cases. Therefore, P must be restricted to positions where x less than or equal to 5 over 3a. And we've done the calculation, and provided that's true, the tension will be less than or equal to 5 mg. If you go beyond it, then it will be greater than 5 mg. So there we go. Just want to reiterate, that is one of the tougher ladder kind of problems. we've had to work algebraically for much of it. We've got, ropes, we've got walls with friction and normal reaction. We ended up looking at the resultant. We've got a weight on the plank. Um, but if you get a good diagram, actually, the first part does come to, it looks really complicated, but it came together really quickly by taking moments about A. And then we got into the normal strategy. I mean, it guided us along. That was one thing about this question. It does help you out a bit. But the normal strategy of, yeah, resolving vertically and horizontally. We were looking at the horizontal first, and that allowed us to work out what X was in terms of A. And then we looked vertically, and that allowed us to get the frictional force from which we could get the resultant force at the wall, and in particular tan at the angle to the horizontal. The very last part was just saying that the tension can't be more than 5 mg. So we wrote down an inequality going back to the original version of the tension before we'd worked out what X was, because now X is back varying. And that gave us that X is less -5/3a. Phew, well done.